Ahledabad High School and the Junior College. Welcome to the series of the lectures of Intermediate First Year Chemistry. In the last sessions, we have been discussing the different concepts of atomic structure. We have started with the basic subatomic particles, its invention, its discovery, and what are the experiments which are being done for producing these subatomic particles. After that, we have started the different models of atom, that is, we have started with Thomson's model, we have discussed the Rutherford model, right. Before going on to the next model, let us have a glance about the previous thing, that is, what did J.J. Thomson tell? According to J.J. Thomson, the whole atom is something like a watermelon, right, in which he classified the red part and black seeds as electrons and protons, right. And the next part is Rutherford model. He tells that the electrons revolve around the nucleus, right. Then is it true all the time? See here, there are few conditions for a electron to be in circular motion, right. What are the conditions? What is the energy that is making the electron revolve around the nucleus? Was it being explained by Rutherford? No, it is not explained by the Rutherford. Therefore, we can tell that Rutherford could not explain clearly about the energy states of a electron. Is it clear? Once again, let me tell you. We know that for any electron or for any object to be in circular motion, there should be some energy or the some force which is making the electron revolve around it, right. Is it true in case of electron? No, he could not explain about what is the energy state of that, right. Because of that, the stability, the atom loses its stability, right. That is what we can tell in the drawbacks, that Rutherford could not explain the stability of an atom, and he could not also specify that a charged particle radiates energy, right. We always know that when a particle moves from one point to another point, right, whatever the charge it is, the charge moves, the energy is being radiated, isn't it? Is it clear? Then he could not account for such things, and he did not even explain about the electronic distribution around the nucleus. Clear? He told that the electrons revolve around the nucleus, but he could not specify how many electrons revolve at the same speed or in the same distance, right. Who knows, the electron may be at some distance or it may be some other distance, right. Based on that, we know that there is a size difference. Is it clear? But he could not explain about that, right. These are the basic drawbacks of Rutherford. From these drawbacks, the next model explained was Bohr's atomic model. What was Bohr's atomic model? From where did this Bohr's atomic model come? What are the basic things? What are the basic things that made Bohr to describe a new model, right? What are those things? See here, till now we have seen Thomson, till now we have seen Rutherford, and we have seen the experiments of different subatomic particles, right. Then Bohr's atomic model, what are the basics for Bohr's atomic model? Let us discuss that, then we will go to the postulates of Bohr's atomic model. What are those things? That is, the first thing, he took the basis of the dual character of a subatomic particle, right. The dual nature of any electromagnetic radiation that possesses wave-like particle, wave-like structure and particle-like structure. Is it clear? He tells, he takes the basis of two things. One thing is the dual character of an electromagnetic radiation. What is the dual character? That radiation can have both particle-like nature and wave-like nature. And one more thing is, he tells that whatever the atomic spectra which we take, the atomic spectra which we take to explain the basic atom, that always depends upon the assumption that energy is always quantized. Is it clear? The assumption is very clear, that he always tells that the whole energy is being quantized. What is that quantization? Quantization is very clearly we can understand is, it is produced in terms of quantities. What is that quanta called as? Let us discuss these both concepts. Is it clear? Right. Thomson, Rutherford, and after that Bohr. On what basis did the Bohr decide? Is it clear? On different experiments based on, see here you can remember few experiments such as Maxwell's experiment. See here, this dual character actually it explains that whatever the radiation is there, the electromagnetic radiation can have both wave-like properties and particle-like properties. Let us discuss who proposed that. And the next is, he tells that every atomic model or whatever the atom, it is based on purely an assumption that all the energies which are radiated, right, all the energies which are radiated are always in a quantized way. Is it clear? Let us see what are those two principles. Let us move on to the first, the base of an Bohr's atomic model, that is the wave nature of an electromagnetic radiation. What actually an electromagnetic radiation? See here, we have seen the different kinds of radiation when an electron is rotated around or revolving around a nucleus, right. What are the different things? See here, to understand that, Maxwell was the first person to explain that whatever the charge particle always produces a two different fields, that is a magnetic field and the electric field, always in the perpendicular direction. He tells that the electric field and the magnetic field are always perpendicular to the direction of propagation and perpendicular to each other. This is how a particle moves, right. And we also discussed that in the before theory that light is a basic thing, right, in which we know that Newton was the first person to tell that light always travels in a kind of particle. That particle he tells it as corpuscle. That was the main basic of the Newton's corpuscular theory, right. After that, Huygens was the second person who tells that the light always travels in the form of a wave, isn't it? Then he could modify both of them, then they could start the new thing that the light always travels in the form of a particle and wave nature. Is it clear? Based on that, Maxwell tells that a charge also can have two different wave natures, I mean two different properties, that is particle like property and wave like properties, and among them he tells that this electric field and the magnetic field are always perpendicular to each other and these are perpendicular to the direction of propagation. For example, if this is the direction in which my particle has to move, then if the electric field is in this direction, then for example, if this is my direction of particle, if this passes through in this way, if my electric field, then the magnetic field always passes in this way. Can you understand? Which means this is perpendicular to the propagation of electric field and which is also perpendicular to the propagation of the magnetic field. Usually in diagrams we represent it like this, right. Here the angle should be 90-90. See here, this is the direction of propagation, this is the electric field and this is how magnetic field moves. Is it clear? That is what he tells. And the second, this is the first point, and second point he tells that we have seen light energy, sound energy, right. In the few experiments of your childhood, you would have seen that the sound and the light, always they need a path to travel. For example, we have seen a bell jar experiment, we have two vacuum tube experiments, right, in which the light or the sound cannot travel. But EM waves is not like that. EM wave does not require any vacuum, they can procure through any kind of solid, right. And one more thing is, he explains electronic magnetic spectrum completely with respect to frequencies and wavelengths, right. For example, if there is a thing, then I can classify this whole thing as different frequencies, which means as much we know, we have different frequencies of signals, right, whether it is a radio signal or a video signal, right. Not only like that, it can be a radio wave, X-ray, gamma rays, right. There are different kinds of frequencies, right. Those all together, it is called as electromagnetic spectrum. Is it clear? He defines electromagnetic spectrum as the combination or the group of all different frequencies of energies, that is those frequencies can be defined in terms of neither frequencies or different kinds of wavelengths, right. What is the relationship between this frequency and wavelength is nothing but c equal to nu lambda. What is c here? C is speed of a light in air, which is usually we define it as 3 into 10 power 8 meter per second. This is a constant value of speed of light in air, where nu is the frequency of radiation and lambda is the, what is the lambda? Lambda is the wavelength of radiation, right. And there is one more term, that is wave number. What is a wave number is, he tells that a wave number is a wavelength or number of wavelengths per a particular unit length. For example, if I assume it to be 1 meter, how many number of waves does it pass through in this meter, right? That is usually denoted by per meter, that is the units of meter inverse. Is it clear? Is it clear? What are the different points he explained in this wave nature? He tells that the magnetic field and the electric field are always perpendicular to each other and perpendicular to the direction of propagation. And the next thing is, the electromagnetic wave does not require any vacuum or any kind of space to travel, right? It can travel through anything, right? Next, EM spectrum will have either frequencies or wavelengths, right. What is an electromagnetic spectrum? An electromagnetic spectrum is a group of all frequencies of energies, right. And the relationship between frequency and wavelength, he tells that c is equal to nu lambda, where c is the velocity of light in air, nu is the frequency of radiation and lambda is the wavelength of that particular wave. Is it right? Is it clear? And one more thing, he defines it as wave number. He tells that wave number is number of wavelengths that passes through a unit length. Is it clear? This is how he explains about a wave nature, and let us discuss about the next topic, that is quantization. What actually a quantization? According to Bohr, he assumes that the whole energy, whatever it is being liberated in terms of quantized number of energies, that is the whole energy is divided into few quantities. What are those quantities? Let us see now. Now let us see the second basis, that is a Planck's quantum theory. What is that? According to him, he always describes about an electromagnetic radiation based on few conclusions in his experiments. Let us see what are those. One is, he tells that the nature of emission of radiation from hot bodies. He explains about it. What is a hot body? See here, he considers a complete closed body. He tells that as black body. That is what he explains about black body radiation. He explains about a black body radiation. What actually a black body is? A black body is a hot body which always radiates a heat, right? What kind of heat it liberates? What is the, in what way does it heat liberates? That is what he will explain. Let us take an example of some element or some rod. Let us heat it. If we start heating it, it initially starts with a red flame. If you observe it, then it goes to blue color, then it finally ends up with a white color flame coming outside, that is a normal kind of smoke, right. What is the difference in between the colors? That is, initially it will start with red and finally it will end with white. What is the reason? That is, it always releases, it starts from lower frequency of energy in the starting and it ends up to the high frequency, that is starting from the red color it will go to blue, white and kind of thing, which means he tells that the whole radiation or the amount of radiation, everything is depend upon, or the frequency is also depend upon the temperature. He tells that whatever it is, he explains about the variation of heat capacity of a solid as a function of temperature. These all are the conclusion of his black body radiations experiment. You can see here, as this lambda is increasing, that is for different variation of lambda, here the temperature is suddenly changing, that is for high temperature it has high intensity. For high temperature, even if the frequency is very high, the temperature is, the intensity is very high for high temperature, right. Here it is being very less when compared to this, that is it is slowly increasing and it cannot reach to higher level of intensity even if the wavelength is increasing, right. This is how he will explain about the dependence of the temperature, and he also tells that whenever a light or kind of thing or energy is being projected on a metal surface, the electrons are being evolved. This will again we will discuss in the photoelectric effect. He tells that when a different kind of energy such as a light energy or different energy, when it is being projected on a metal surface, it ejects an electron, right. And last most thing he tells that the whole conclusion or everything or a basic atomic model can be easily explained by a line spectra of an atom, with he takes the special reference of hydrogen atom. Since the hydrogen has only one electron, he could explain each and everything, which means for different frequency of incidence he could find different kinds of reflections. What are the different reflections of frequencies, right? He could draw a line spectrum and he could explain the basic topology of hydrogen. Is it clear? This is how, based on these conclusions, he tells that the different postulates of quantum theory. Actually, what is a quantum? According to Max Planck, he tells that whatever the energy is being released by revolving or even after the charged particles, that energy is always proportional to the frequency of radiation, right. The energy which is being released is always proportional to the frequency of radiation at which it radiates. If we remove this proportional, we get it as h into nu. This h is a Planck's constant whose value is 6.626 into 10 power minus 34 joule second, right. Is it clear? This is how Planck explains his quantum theory, right. Then he explained about energy in different kinds of frequencies, right. He always tells that for this frequency we will have this kind of energy, for this frequency we will have different kind of energy, which means for different quantized frequencies, that is the quantity is fixed. For that fixed quantity, he is telling that the energy is also fixed. Is it clear? And one more thing, he tells that whatever energy it released, it does not released in a complete kind of natural way, it is being released in a quantized way, that is it will release one thing at a time and one more thing at a time, right. Then one thing he defines it as a packet, right. That energy packet is simply called as a quantum, right. If it is more quantums are released, it is called as quanta, right. This is how we explained about a Planck's quantum theory. Is it clear? Hope you can understand what all we discussed till now. In this session we discussed about the basis of Bohr's atomic model. Before that we discussed about the Rutherford atomic model, then the basis of Bohr's atomic model. That is, he always tells that the whole thing is depends upon the wave nature. Is it clear? That is dual nature. Whatever radiation, that always possesses two behaviors, that is the first behavior is it can have a wave like properties and also it can have particle kind of properties. Is it okay? That kind of properties are being examined to give a Bohr's atomic model, right. And one more thing, he takes an example of Planck's quantum theory, right, through which he could explain different line spectrum and the atomic spectrum. Is it clear? Okay. After this, let us have a small introduction about how the ejection of electrons are being taking place from a metal surface when a light is being incident on that. Okay, let us discuss that. See here, whatever the metal it is, if I take some metal, okay, if there is some light is incident on this, let us have the energy of that is E. Okay, when a light energy is being incident on a plane surface of a metal, remember the surface should be plane, right, even if it is textured in some way, texturing in the sense some kind of indisturbance, that is non-uniform surface. If a surface is completely plain and uniform, then a beam of incident, I mean a beam of light is being incident on the surface, then it ejects an electron, right. Why does it eject, right, that was the conclusion of that, right. Why does that eject is again a different theory, let us discuss that. He concludes that when a light energy or a beam of light energy falls on a plane surface, then it ejects an electron. Then what could be the radiation of energy? That is, since it is being ejected, say here remember there are two things to remember, that is the potential energy and kinetic energy of any electron in it. This electron is being given, already it has a potential energy. Why? Because it is being rotating I mean it is being revolving around a nucleus, then it has to be removed outside. It needs some energy, we give that energy. There is the basic thing which we have to remember in the further topics, right. He tells that this energy is being radiated after getting some kind of energy. It has some energy such as h nu, right. It needs some more energy. If the energy is released as h nu naught, right, released in the sense if it accepts some h nu naught kind of threshold energy, once it reaches such energy, it will get excited and it comes out with an energy of half mv square. Is it clear? From this, Max Planck tells that this is a kind of photoelectric effect. Is it clear? Once again let me tell you, it initially has some h nu of kind of energy. It should cross its threshold value. What is its threshold value? The minimum amount of energy. He always observes that, see here, he tells that on a plane surface, when a light energy is being incident on that is a beam of light energy is being incident on a metal plane surface, then within no time this electron will come outside. There is no time lag. But one thing we can see here is there is a kind of little energy required more. Say here, the energy may require for example, even there are different kinds of metal we can see here, but there is no kind of electron is being released. Why? Because the amount of energy needs to cross some particular value. For different metals will have different kinds of threshold voltage. Okay, if it reaches the threshold voltage, then only it ejects an electron. Is it clear? This is how he explains about photoelectric effect. And one more thing is the dual nature. We already discussed that the dual nature is a radiation can be either in the particle way or in the wave nature. Okay, is it clear? This is for today. Let us discuss a few more topics of this, which means what are the basics and everything, and let us discuss this line spectrum, right. Let us discuss such kind of things in the next class, and we'll start with the Bohr's atomic model. Is it okay? Is it clear for today? Fine. Let us discuss few more topics of atomic structure in our next class. Is it clear? Thank you.